Se ci mette un po' a iniziare a registrare. Ecco qua. Okay, very good. I was just talking about how few, the number of students has decreased dramatically, which is a pity because, I mean, of course, I would enjoy it most, to be there, because it's even, for some reason, it's even faster when I'm using the Blackboard. So I'm about two lectures behind. So we'll see what happens. Anyway, so you might have noticed in this course that there is a lot of analytical approaches, mathematics. Well, don't be too surprised, okay? I mean, I just want to take a minute here. Combustion nowadays is essentially numerical, okay? Numerical combustion. So we heavily use computers, okay? Of course, there is an experimental side as well, of course. But now computers are catching up to the extent that now we can simulate directly very small but very significant, okay, combustion processes, especially turbulent combustion processes, and generate huge amounts of data. And it is very important that you realize that these basic notions that we're doing now, that we're looking at now, are really now ingrained and fully part, okay, of the algorithms that are being used nowadays to solve to solve combustion problems. To tell you one thing out of the many, I mean, possibly the most important, what we're doing right now is the timescale characterization of non-equilibrium kinetic processes, right? Now, if we didn't know anything about this, so if we hadn't studied combustion processes using these approaches where we actually highlight, okay, the separation in timescales, we wouldn't be able really to apply an effective integration algorithm. I mean, in the 70s and 80s, numerical analysis has developed these algorithms, integration algorithms that in time, okay, that deal with stiffness, okay? And stiffness is a very, very big problem because when you have very separate timescales and you have timescales that are the interest, okay, of the timescale is of the order of 1 second, let's say. So this is the timescale that you're interested in. Let me see what happens in 1 second of combustion. But really, if you look at all the timescales, the smallest one is maybe 9 orders of magnitude less than your time frame of interest. And so it would be absolutely impossible to integrate this phenomenon using an explicit approach, for example, okay? So you really need to construct a series of techniques that will simplify the problem, okay? Or, as we say, reduce the complexity of the problem. One other thing is the number of reactions, okay? We know that the combustion process of a typical hydrocarbon is comprised of thousands of reactions, okay? Which involve a huge number of intermediate species, okay? Radicals, we call it, okay? Now, to feed that huge mechanisms into a computer is usually intractable. So we tend to want to reduce the number of reactions to within a tractable number, okay, maintaining the accuracy. So that's the challenge, okay? So these are all challenges that have been, let's say, involving the community, the combustion community, for the past maybe 30 years, okay? And now we have come to a point where we can really solve the Navier-Stokes equations in a turbulent scenario, and a reactive, okay, in their reactive form, not just resolving every single spatial time scale. Okay, so maybe flame thicknesses, but even smaller than that. If you have, for example, very high Reynolds number, you may have a very small turbulence scale called, you may have heard, Kolmogorov scale, but also the temporal, okay, aspects. So all the time scales. Okay. Now, I consider this a very important part of the numerics involved in combustion. Okay, without which you really don't understand, okay, what's going on. I mean, why are flames very thin? Why do combustible mixtures actually explode? Okay, this is it all has to do with the concept of timescales, which again come from essentially in chemical kinetics, the exponential term, okay, in the Arrhenius reaction rate formulation. Okay. Now, to understand things even further, we have already seen a lot. Okay, we've seen a set of ordinary differential equations treating a kinetic system, and we've seen a little bit of the characterization of the timescales. We have defined essentially the temporal boundary layer. So when there is a separation of timescales, we introduce the small number epsilon, okay, which measures the ratio of the fast to slow timescales, and we've introduced the concept of singular perturbation, or singularly perturbed form of our ordinary differential equations, where you separate essentially the fast and the slow species, and you introduce this small number epsilon. Now, to really understand this fully, I think we should look at linear systems, or better still, linear dynamical systems, or linear systems of ordinary differential equations. Okay, of course you've seen those. You've seen those many times. Some of you may have seen them a little bit more in depth than others. So let me just recap a little bit of the main concepts. We're dealing with linear systems because they are tractable mathematically, okay? But of course, ultimately, we are interested in non-linear systems, okay? Because every single, except for very, very specific problems, every single chemical kinetic problem is, of course, non-linear, okay? So we've seen some linear kinetic models where we assumed that the rate constant is just a number, is constant, okay, and maybe you have first order reactions, okay, but generally speaking, you have a nonlinear system. So linear systems will give us at least the mathematical framework, and will tell us a lot about timescales and how we can define them, okay? So let's take a look at linear systems first. What do I mean by linear systems? So we're talking about ordinary differential equations. So, well, we're not starting very well with the handwriting here. So consider a vector of dependent variable x, okay? We can write it down as x dot, okay, to express the rate of the derivative with respect to time. Okay, if it's linear, the system of ordinary differential equations can be put into this form. So you have a constant coefficient matrix, okay, and then multiplied by the vector of unknowns, okay, so the vector of dependent variables. So A is a matrix which is constant coefficient, right? So it's just a matrix of numbers. Of course, to this we have to add the initial condition, which is something like this, for example. Okay, so this is the generic form of my linear system of ordinary differential equations. Now, For those systems, there's a full theory. It's a closed theory in the sense that we know everything about it, okay? First of all, what's the solution? Well, you have a solution, we call it operator, okay? Sometimes we can call it, well, phase flow. These are, this terminology is essentially dynamical systems, okay, terminology. So some of you may have done some dynamical systems, okay? So essentially systems that are governed by sets of ordinary differential equations. Generally speaking, clearly, they're nonlinear, okay? And what's the solution operator? Well, it's an operator that maps the initial condition to solutions at time t. So we write it, the solution at times t, we write it as x of t, okay, is mapped, okay? So the solution at times t, okay, is recovered by mapping, okay, the initial condition x0, okay, with the use of an operator. What's this operator? It's the so-called matrix exponential. So it's a matrix, okay? We call it matrix exponential. That has some properties. I'm not going to go into all the details here, but it's essentially an exponential to the power of this matrix A, okay? And it's itself, you have to consider this as being a matrix. So it's a matrix, or if you will, an operator whose matrix is this, okay, which maps, okay, which applied to the initial condition will give us the condition at times, the solution at times t. So in fact, okay, sorry, you have an initial condition x0, which is maybe a point in the phase space. You have the solution, which is a trajectory, okay, in the phase space, and here you have essentially your solution at times x. And to get from x0 to x, you use this matrix exponential, which is fully known, okay? So it's an analytical solution. The fact that this is the solution is straightforward, because if you differentiate this expression here, if I move around with the cursor, can you see it moving?
No, Professor. This is the issue. We can see only the mouse pointer.
Okay. What do you mean you can see the mouse pointer? Then can you see it moving?
Yes.
Now you can, but now you can't, right?
No, I can.
Okay, so I understand. So you see, if I'm using the pen.
Exactly.
Okay, but if I use this, then you can. Okay, fine. Okay, it's a little bit. Okay. So, so if you. Sorry. Okay, if you look at the solution operator and you differentiate it with respect to time, you have something like this, right? You have a e to the at times the initial condition, okay? And clearly this is your solution operator, so this will be a times x of t, which is exactly your initial system. So it identically satisfies your system of linear ordinary differential equations. Now, how do you represent this matrix exponential? Okay, this matrix exponential here, a to the t. Well, you know that A has certain spectral properties which are manifested in the form of eigenvectors, right? We call them right and left, okay, eigenvectors. So let's define their properties, okay? So the right eigenvectors, we can store them, we can place them in a matrix, okay? So we can call them V1, V2, okay, Vn. Okay, why is this a matrix? Well, because you have to think of essentially V1 as being a column vector. Okay, so the first column is the first column vector. Okay, the second column of the matrix is the second eigenvector, and so on. Okay, so the overall we have a matrix. Okay, so this is the matrix of right eigenvectors. Now, its inverse, okay, is actually the matrix of left eigenvectors. The fact that we call them right and left, you'll see in a second. It's very straightforward, okay? So, how can we represent these? Well, still with this notation, they will be different, clearly. We will use a superscript instead of a subscript. I won't go into too much detail here, but we're introducing the so-called variant and covariant notation, okay? But the truth of the matter is, if we write it like this, okay? Okay, with a transpose here, what you have to think of this is essentially a vector, okay, transposed. So this is actually a column vector, okay, of vectors, okay? So essentially it's a matrix, okay, of the following kind. So each of these vectors here, W1, W2, Wn, are actually row vectors, okay? Like this. That's all it is, okay? And this is the matrix of left eigenvectors, okay? So what are eigenvectors? You know, by definition, if you multiply A and an eigenvector, Vi, okay, what you have essentially is another vector which is parallel to Vi, okay, and is amplified or shortened by a factor lambda, which is the eigenvalue. This we know, right? And finally, I think what the scope of this lesson is to finally understand what the physical meaning of eigenvectors and eigenvalues actually is. Okay, and we'll give a geometric representation of eigenvectors and eigenvalues. Okay, but essentially eigenvectors will be directions, invariant directions in the phase space, and eigenvalues will be a measure of the time scales. Okay, but we'll see this later. So in matrix form, something like this means that if you multiply A, okay, with the matrix of right eigenvectors, so V1, V2, etc., Vn, okay, you'll end up essentially with the following matrix. You have lambda 1, V1, lambda n Vn, okay? This is by definition, okay? So how can we write this in matrix form? Well, this is A that multiplies, well, this matrix here, we called it R, so it's the matrix of right eigenvectors, will be equal to essentially still the matrix R times a diagonal matrix lambda, where the diagonal matrix lambda is nothing else but the matrix of eigenvalues, okay, which are placed on the diagonal. And here you have essentially just all zeros, okay? So it's just a diagonal matrix of eigenvalues, okay? And in fact, if we now pre-multiply by the inverse of R, okay, we essentially have an overall expression, okay, telling us that if you left multiply, so you see here R minus 1 by by this R minus 1, and you right multiply by R, so that's why we call them left and right matrices of eigenvalues, you have essentially the matrix of eigenvalues, so the diagonal matrix of eigenvalues. So this is essentially an overall expression, okay, defining essentially eigenvectors and eigenvalues, okay, in matrix form. Now, we haven't yet said anything about the matrix exponential, right? E to the AT. How do you write it, okay? You can prove that this matrix, okay, E to the AT has, okay, the same eigenvectors of A. Okay, we're not going to prove this, but it's easily seen. Okay, and has eigenvalues that are not lambda, but are e to the lambda t. So the set of eigenvalues is this group here, e to the lambda it, where I goes from 1 to n. Okay? What does this mean? Well, essentially, it means the following. Look at this expression here. Well, it has the same eigenvectors. So if we left multiply, okay, by the left matrix of eigenvectors, the matrix exponential, and we right multiply by R, well, we should get here a matrix which is diagonal, and on the diagonal we have essentially the eigenvalues, but the eigenvalues are e to the lambda t. So you see we will have essentially a diagonal matrix which is of this form. Okay, we can call this the matrix e to the big lambda t. Okay, e to the big lambda t is essentially a matrix whose diagonal members are the exponentials of the lambda I t's. So they are the eigenvalues of the matrix exponential. Okay, I'm giving you a very short version of something that we should prove, but clearly, intuitively, it's rather straightforward. In fact, if we can write this expression here, what you can do now is multiply by r. So you see that now r to the minus 1 is the identity matrix. So ATR is equal to r e to the lambda t. Okay, and we right multiply by r to the minus 1. And so we have essentially a form. I hope you followed this. So remember that r to the minus 1 is the identity matrix. Okay, I'm not even saying this. Can you all see?
Yes, Prof.
Okay. So I'm pretty sure that most of you somehow you've seen this in the past. Okay, if you're not, obviously, if you haven't seen it in matrix form, you have definitely seen it in scalar form. Okay, so that means that we can write down an expression for the matrix exponential. It's this big matrix. Here are e to the lambda t r to the -1. So if we know the matrix A, we know the eigenvectors of A, the eigenvalues of A, so we can construct both R and this matrix here. Okay, and we can write down everything. So essentially, remember, we had our original system, which is our set of linear ordinate differential equations, okay? It has a solution, which is x of t equals e to the at, mapping the initial condition, okay? So now we can write this as, since now we have an expression for the matrix exponential, r e to the lambda t r to the -1, which maps the initial condition, okay, x0, okay? So let's write it in full. Well, R is, remember, the set of column left eigenvalues, okay? Sorry, right eigenvalues, sorry. Sorry, not n, to n. Okay, then we have, so this is R. Now we have this matrix here, which is essentially the diagonal matrix containing the exponentials here of the eigenvalues to e to the lambda t, and then we have the matrix of left eigenvectors, which is, again, remember, it's a column matrix. Okay, everything multiplied by the initial condition. I will leave this in vector form x0. Okay. So now we use essentially the matrix multiplication. So this is r to the -1. Okay. We use the matrix multiplication. How does it work here? Well, V1, okay, let me just, V1 will multiply the first member, V2 the second, Vn, okay, the nth diagonal member here, okay? So in fact, we have the sum, okay, on I, from I to n, of our vectors Vi times e to the lambda it. Okay, what about this last bit? Okay, well, this is simply well, it's the application. Okay, so remember, these are this is a little bit more technical here, but remember that W's are row vectors, okay? And X is a column vector. So you're actually multiplying all the components of W with all the components of the initial vector X. So what you're doing here is you're multiplying this by this, the second by the second, and the last by the last, okay? It's not a scalar product, okay? It's more like an inner product, okay? So how we write it is we write it as Wi, okay, applied to. I'm putting the vector sign either on top or at the bottom. Okay, it's the same thing. Okay, and x to the 0. Okay? So we have now written in full, okay, the solution to our system of linear ordinary differential equations. Okay? And in fact, it's a very interesting form of the solution. Because look, first of all, x, okay, you can think of it as a trajectory, okay, in the phase space, okay? So that's x of t, okay? Clearly, this is a vector, so this is the vector joining the origin, okay, with a point on the trajectory, okay? I hope this is clear. If it's not clear, tell me. I mean, I'm just trying to draw straight lines here. So you have a point, okay, describing a trajectory in your phase space, okay? And clearly, this is a vector, so it's composed of all components. So it's essentially, each point is essentially of the trajectory is characterized by coordinates, which are the components of x, okay? Fine. Wait, this is too big, okay. Now, x, as you can see, is the sum of two parts, essentially. Okay. Now, this part here represents the projection of the initial condition x0, okay, onto the, so you see that there's an I here, onto VI, okay, the ith eigenvector, okay? Generally speaking, VI are independent vectors, okay, but they're not orthonormal. So to actually have the projection of any vector onto the spaces, you need the so-called dual basis. So the dual basis is essentially the W's, okay, the left eigenvectors. But bear with me. I mean, you know some, if not most of you, will know a lot of linear algebra, okay. When you don't have an orthonormal basis, well, you have these dual basis vectors here. And what they need, what you need them for is to find the projection. So W applied to x0 means that you're measuring the projection of x0 onto VI, okay, the dual. Okay? And each projection, okay, each of these projections evolves like this. So evolves, projections evolve, well, first of all, with a time scale, which is 1 over lambda I, okay? Here it is. And not only that, but it will evolve along this direction, along a direction which is exactly the eigenvector VI, okay? And that has a lot of consequences, okay? A lot of consequences, because you can think of the dynamics, okay, of your ordinary differential equation, which is essentially your trajectory, as being essentially composed of n different directions, okay, each having, along which, okay, the system will have its own time scale. So let's see what we mean. For example, suppose we choose the initial point, x0, okay, to be equal to an eigenvector. Okay, so essentially, well, to simplify things, think of the plane. Okay, okay, and you may have two eigenvectors. Okay, so this would be vk. Okay, and this would be some other. Okay. So these are the two eigenvectors on this plane. So we choose x0 somewhere here. Okay, the initial condition is along this direction here, which happens to be an eigenvector of A, okay, of the matrix A. Well, remember, R to the minus 1 is the identity matrix, okay? This means that if we apply Wi, okay, to Vj, okay, W is essentially the dual of V, okay? It's essentially the members, the row members of the inverse matrix of R. Then clearly, because this is the column members of R, we will simply have delta ij, where delta is the Kronecker delta. So it's 0 if I is different from j, and it's clearly 1 if I is equal to j. Okay? I hope this is straightforward. Okay? So clearly now, if we choose the initial condition as being vk, okay, and we substitute it in here, okay, well, we're going to have that x of t, our solution. So look at the solution over here, okay. We still have the sum on vi, e to the lambda I, but then we have wi applied to x0, which is vk. So it's very simply delta ik. So obviously now, all of these terms are all 0 except for the kth term. So we have only left vk e to the lambda k, and that's it. Only one term survives. So what does that mean? It means that if we choose the initial condition as being lying on an eigenspace or an eigenvector, and not on other, not as a projection of others, but exactly on one eigenspace, the solution vector, you see, x of t, is always parallel, always lies along vk. It will decay or it will explode depending on whether lambda is bigger or smaller than 0, okay? But for every time, for all t, okay, x of t okay, is, well, we can say parallel, but it's actually is in, okay, vk, meaning that it's actually vk multiplied by some constant, okay, or some factor, okay. So we say that vk represents an invariant subspace under the dynamics of x dot equals ax. Okay, so essentially, I hope you got the concept here. Okay, let's go back here, okay? We are choosing an initial condition lying exactly on one of the n eigenspaces, okay? The dynamics of our ordinary differential equations, of our dynamical systems, will be such that this will move clearly, maybe along here, or even towards, okay, this point here, okay? But it will never leave, okay, Vk. So in this sense, Vk is invariant, meaning that the dynamics, okay, of our system always maps Vk onto itself. So these are special directions, these eigenvectors, okay, of the matrix A. And they're special because they're invariant. They're like the backbone, okay, of the dynamics. The dynamics is composed of all these VAs, okay? So it's like a vector space that generates the dynamics, every single dynamics for every single initial condition that we have in our system, okay? So that's why when you have an operator or a square matrix A, it's so important to define eigenvectors and eigenvalues, because indeed the speed with which we're actually moving along this, okay, will depend on the eigenvalue. And it makes a huge difference if the eigenvalue is actually positive, because then it means that the trajectory will just explode away from the origin indefinitely, okay? It will diverge for infinite times, or if it's negative, okay, it will converge to zero, okay? In fact, one thing that maybe I didn't say is maybe the most important one. Given a linear dynamical system, x equals 0, okay, so the origin is actually the only existing equilibrium point. Why? Because, well, substitute x equals 0 in the system, you see that when x equals 0, x dot is equal to 0. And therefore, if x dot is equal to 0, the dynamics is at equilibrium, okay? Because the derivative in time, it's stationary. It's 0, so it's a stationary point. There's no other equilibrium point. And in fact, having said this, if we now define the eigenvectors and most of all the eigenvalues, if one of the eigenvalues has a positive, is real and positive, okay? Forget for the moment the special cases, okay, where the eigenvalue can be 0, for example, or even a complex number, okay? For the time being, we'll just consider them as real numbers, either positive or negative, okay? But if it's positive, then you know that the equilibrium point has an unstable character. If they're all positive, the origin is an unstable point, okay? But in fact, we'll be clearly interested in stable points, because think about it, we want to talk about chemical kinetics, and you know that at equilibrium, it's obviously not going to diverge to infinity. It's going to converge to an equilibrium point, which is actually the composition of equilibrium, of thermodynamic equilibrium. So we have a finite point where all of the components of these points, all of the coordinates of these points are real numbers, clearly, and they are all positive numbers. And it's not going to be somewhere at infinity, clearly, okay? Because we have to conserve the mass, of course. So it's a physical problem. So when you try and now focalize on the physical problem, now clearly all of our equilibrium point will obviously be a finite sort of equilibrium point, okay? Now, so in general, VK, what we can say is we can define, this is just a pedantic kind of definition. VK is a vector, right? So this VK is a vector. So if we define the corresponding eigenspace or vector space, we can write it like this. EK is the span, okay, generated by VK. So what we're saying here is you take a basis, which is our, in this case, is just composed of one eigenvector, and this will generate this eigenspace, which we call EK. So EK and VK in this case could coincide, okay? But this is just a way to define the concept of eigenspace, okay? EK. So generally speaking, in your phase space, okay, you're going to have starting from the equilibrium point, okay, eigenspaces like EI, EK, and so on, okay? So, and they're all spanned by, let's say, vectors. You can call this vectors or unit vectors because clearly the eigenvectors are known to within a constant. So essentially, you can normalize them to one, okay? And of course, again, if you take an initial condition, x0, what we've learned is that after some time, okay, the solution will move, okay, along these directions, okay, xt. In this case, it's moving away from the origin, okay, in this case. So this would be associated to a positive eigenvalue, okay? You can take the initial condition, for example, here, and we know that after some time, it will still be on the eigenspace EI, okay? And in this case, lambda will be negative because you see it's moving towards the origin, okay? So it's e to the minus lambda, e to the minus something t, okay? Now, we know really everything we need now. Suppose that you have a two-dimensional system composed of, so we have two eigenvectors, which we will identify with the subscript U for unstable and V for stable. Okay? So essentially you have the two eigenspaces EU and ES. Okay? The U stands for unstable. So lambda U is positive, and S stands for stable. So lambda S is negative. Okay, suppose now I want to figure out what the trajectory is, okay? The solution of our system is. Well, remember that we know the solution. Okay, x of t, okay, will be composed essentially of what? Of two terms, okay? We have e to the lambda s t along the direction vs, okay? And the initial projection along of the initial condition, which is ws applied to the initial condition, okay? So I'm just rewriting down the analytical form. And then we can do exactly the same with the unstable case, okay? So the unstable, okay? And then the initial projection, which is WU x0. Okay, so what's going on here? You take the initial projection along the two eigenvectors is stable and unstable, and you evolve them along these two directions by these factors here, e to the lambda st and e to the lambda ut. So we can do this absolutely graphically here in the following way. So suppose this is ES, okay? And this is EU, okay? And suppose the initial condition is here. This is x0, okay? Now, what you want to find now, first of all, is these two projections. The projection of the initial condition onto the two eigenspaces. So what you do graphically is you project. Clearly, this is not an orthonormal basis, so the projections go parallel, okay, like this. So what this means is that this quantity here from the equilibrium x equals 0 to here, this will be what? It will be the WS x0. Okay, so this is the projection of the initial condition onto VS. Okay, and this amount here will be the projection of x0 onto VU. Okay, which is WU x0. Okay, so we found this term here and this term here. Now, what we know is in time, for positive time, they will now, these projections, this projection here and this projection here, will evolve along with these timescales, lambda s and lambda u. Okay, so we said that lambda u is positive and lambda s is negative. So starting from here, because lambda s is negative, we're moving along ES, and this will shrink. Remember, because lambda s is negative, so it's e to the minus something t. On the other hand, this point will move up because lambda is positive. Okay, so in fact, our next point will be something like, well, like this, and then after some time, you will have this situation here, and then this situation here, and so on. So by joining these points, you see that you have something like this. Okay. In fact, if we had started from here, okay, you see it's a curved trajectory. We'll put an arrow here. And this is the typical situation where we call the origin a saddle, okay, because it has one positive and one negative eigenvalue, okay. So if we are to draw it schematically, no, if I do it too fast, then when you have a saddle, you have situations like these, okay, where the trajectories follow these paths here. Okay. Now, the amount or the speed with which this shrinks or this explodes here will depend on the magnitude of our eigenvalues, lambda u and lambda s. Okay. So generally speaking, we can have a stable manifold or a stable eigenspace if lambda s, as we said, is negative, and an unstable eigenspace if lambda u okay, is positive. But these could all be all negative. So the next step would be, okay, let me see how big they are. Okay, these eigenvalues, which represent time scales along invariant directions or along these eigenspaces, let me see how big they are. So suppose all of the lambda i's are real numbers. Okay, forget the fact that, and in fact, let's suppose also that not only they're real, but they're also different from zero. Okay, forget the 0 point. In this particular case, we call those systems hyperbolic systems. Okay, I guess essentially because these trajectories are hyperbolic. Okay. Give me one second. Okay. So, as I said, let's perform an analysis to understand how big they are, okay? How big these numbers are. So what we can do is we can perform, you can still hear me, right?
Yes, Prof.
This is what we wanted to do from the start, understand timescales, whether it's the system is stiff, whether the timescales are far apart, which is the driving timescale, which is the fast timescale, which is the slow timescale. That's what we're doing. So we order them. We order those eigenvalues in this particular way. This is obviously arbitrary, but we call now lambda n, okay, the smallest, okay, and lambda 2, lambda 1, okay, the largest. Okay, including signs, okay? So this could be, for example, negative numbers, okay, and these could be positive numbers, okay? As long as you order them, okay? I'm not ordering them in magnitude. I'm ordering them in magnitude and in sign, okay? So we make this ordering, okay, which is pretty arbitrary, okay? And now we can rewrite the solution in the following way. So remember, the solution was what? Was vi e to the lambda it, and then the initial conditions, right? The projection on the initial condition. So we can, this is a sum, okay, of n terms. What we do, we can take e to the lambda 1t outside, okay, so that inside we have this following situation. Well, first of all, the first term, which is v1 w1 x0, okay, and then what we have here left is a summation of the rest of the eigenvectors vi e to the lambda I minus lambda 1, right? T. And then the projections. I hope you agree. What's the nice thing about this? Well, think of this. Because of the ordering, okay, this is lambda I minus lambda 1. Okay? Because of the ordering, by definition, this is negative, right? So, for long times, the asymptotic behavior, okay, this factor will tend to 0, right? Because lambda I minus lambda, this is not I, yeah? This is 1. Oh, God. Lambda I minus lambda 1. Okay? This number is negative. So e to the negative something, t, will clearly tend to 0 as t goes to infinity. Okay? So we have figured out that the asymptotic behavior of our system, x dot equals ax, okay, is, okay, so by asymptotic, but we mean t going to infinity at long time, is x of t going to, well, if all of this will eventually go to 0, is simply e to the lambda 1 t v1 w1 x0. Okay? So what do we mean by that? We mean that the trajectory for very long times, okay, will align, will go towards, okay, the dominating direction. And the dominating direction, okay, is the one that is associated, okay, to the greatest or biggest eigenvalue, which in fact we called lambda 1 because of that ordering, okay? So I hope you understand this. This is possibly the most important aspect of today's treatment here. The timescales are all associated, or they all coincide essentially with the eigenvalues, in fact with the reciprocal of the eigenvalues. But so they're all scalar, these are all numbers. You can order them from the very small, maybe minus 100, okay, to the largest, which could be 10 or 5 or minus 1, okay? You can order them. Clearly, the minus 100 is a very stable timescale in the sense that it's associated with e to the minus 100 t. E to the minus 100 t very fast goes to 0, okay? On the other hand, e to the minus 1 t will go to 0 much slower, okay? So, the dominating both direction, so eigenvectors and eigenvalue, is associated with the largest, okay, eigenvalue. That's the most important lesson to be learned, okay? How can we see it graphically? Suppose that I have two eigenspaces, E1 and E2. Okay? And suppose that we have this ordering here, minus 10 and minus 1. Okay? This is lambda 1 and lambda 2, clearly, because we have ordered them so that lambda 1 is the largest and lambda 2 is the smallest. Okay? And suppose that we have our initial condition over here. So we know now the trick. Okay, we project the initial condition on the two subspaces, okay? So this is the projection of the initial condition on E1. This is the projection on E2, okay? Now look what happens. The initial projection on E2 will decay with a time with e to the minus 10t, and lambda 1 will decay to the e to the minus t. Okay, so after the unit time, we'll have a huge decay, maybe, I don't know, here, okay, for e to the minus 10t, and maybe here, okay, for the initial projection on E1. Okay, so now essentially we have this situation here. After some more time, we're going to have something like this. Okay, and so on. So at the end of the day, you see that our solution, which started off like this, okay, is now converging, is more and more parallel to the dominating eigenspace, okay? Maybe I should have made them a little larger like this, but you can see that now what's going on, right? So this is x0, okay? The vector associated to x0 is really collapsing onto the most unstable or dominating eigenspace. So when you can do all sorts of examples here, and you can play around with this sort of approach. Okay. So we have the following classification. If you have the real line, okay. Suppose that actually we have a 0 here. We said that we have to order them like this. Okay, so suppose we have a bunch of eigenvalues. We order them like this, lambda 4, lambda 5. Okay, so this would be, I don't know, some minus 10, minus 7, minus 1, 1, and 3. Okay, something like that. And this is 0. So I was pointing it. So minus 10, minus blah, 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 1, and 3. Okay. This guy, okay, is what we call the dominating subspace. So E1 associated, so it's the most, we call it unstable. The most unstable, okay? Largest eigenvalue. By dominating, we mean essentially that for t going to infinity, the asymptotic solution will converge towards E1. Okay? Clearly, if this is 0, these are all unstable, right? Unstable subspaces. Because lambda is positive. And of course, all of these are stable. And this will be the most stable. Okay? You can also have a situation where you have the same kind of stuff, the same kind of classification. Let's keep this, this 0 here. So you still have the real line. Okay? But now, for example, suppose that all of the eigenvalues are negative. Okay? So which one is the driving one? Okay? The dominating one is still lambda 1. okay? Now, in the previous case, we saw that this direction here was going towards essentially instability, right? Because it's associated with positive eigenvalues, so you diverge, you go away from the initial condition, you go away from the equilibrium point. And this direction here is the direction of stability. Okay? The further down the stability line you are here, you have more negative eigenvalues, and so you're going towards the equilibrium point faster and faster because it's going to be e to the minus 100t. You're going really fast, decaying really fast towards the equilibrium. Now, clearly, if all of these eigenvalues are stable, okay, okay, how do you call the biggest and the smallest? Okay, lambda 1 and lambda n. Okay, well, think about it. They will all decay, they will all be stable, so they will all decay towards the equilibrium point. But what they will do is that they will decay at different rates with different speeds. And so the dominating subspace, in fact, is actually the slowest because it's associated with the largest eigenvalue. Bear in mind, not in modulus, okay, but in sign, okay? So this would be e to the minus 1 times t, and this guy would be e to the minus, sorry, and this guy here will be e to the minus 100. So this would be really fast, okay? So you can actually have a separation, okay, for example here, so that you can call these fast, okay, subspaces. So meaning directions that are associated with very fast timescales, and here you have slow subspaces. Okay. And there could even be a gap here, this gap here. Okay. So for example, this would be associated with something like e to the minus 1t, and this would be, I don't know, e to the minus 100t. Okay. Just to give you an example. Okay. Now, if there is a gap, a so-called spectral gap, this means that this particular system evolves according to two sets of timescales. A slow set of timescale, which represents the dominating, okay, modes of your dynamics, and a set of very fast subspaces. Okay? We got to a point where we're sort of getting near to the physics of combustion now. So even though we're talking about linear systems, again, with linear systems, we can really write down a theory, a complete closed theory. And so in combustion, we said we have, generally speaking, we have very fast and very slow processes, okay, or slower processes. So when you do have this kind of gap, the system is by definition stiff. So gap essentially means stiffness. You can also say spectral gap. The spectral because spectral properties of a matrix A is its eigenvectors and eigenvalues. Okay, so if you have a gap in the eigenvalues, you have a spectral gap. Okay? Is there any way in which we can measure the size of this gap? Okay? Well, yes. look at this picture here. The gap is essentially between lambda 1 and lambda 2, for example. And so we can say that we can define a small number, for example, epsilon, okay, which is 1 divided by the modulus of lambda 2 over 1 divided by the modulus of lambda 1. What does this mean? It's essentially, this is among the fast time scales. See, these are the fast time scales. It's the slowest. So it's the slowest of the fast time scales divided by, well, we could even have another one here, but clearly this would be the fastest of the slow. Okay? So you see now that we're getting closer to the point where we actually even defined an epsilon. Remember the epsilon that came up in the definition of the singularly perturbed form of our system, okay, at the end of the last lesson. So epsilon is a very small number, okay? Bear in mind, I have here taken the modulus in the sense that this could even be positive or negative. So we have to, irrespective of that, we have to, we don't have to have an epsilon with a sign. That's basically it. Very good. Now we have a separation. So let's kind of see what kind of dynamics we can have. Okay, so for simplicity, let's consider two cases. Okay, this is 0. So this is the ordering of our eigenvalues. Suppose that we have a stable and an unstable eigenvalue. So lambda 1 and lambda 2. Okay. So which is the dominating direction? That one associated with lambda 1. That's the dominating one. What does it mean? It means that if I have my phase space, okay, suppose that I have, oh my God, the direction, oh my God, E1, okay, which is associated to the unstable one, and I have, it's really, really, really difficult. So this is the other eigenspace, E2, which is, again, stable. One thing you can do right away is put some arrows on it, saying that essentially, if you are on a stable eigenspace, the trajectory will tend to the equilibrium point. If you're on the unstable, they will tend to infinity away, okay? And we know that eventually this is the dominating one. So at very long times, all of the trajectories will be essentially attracted, or they will collapse onto the unstable one. So this is what's going to happen. These are the the trajectories, okay? And they will all kind of go towards the unstable one. Like this. I'm really sorry that I'm not a very good, these are supposed to be straight lines, okay? So hopefully you've got the point of it. Now, the situation where we're more interested in is a situation where both of the subspaces are stable. So suppose that this is lambda 1 and this is lambda 2. Okay, so this will be the slowest. Okay, dominating. How do we see this? Okay. So suppose, let's see if I can do this a little straighter. No, I can't. Wait. Let me just try something. Oh, God. No. Okay. Okay. I'm using a a trick. Okay. Okay, at least these are a little bit more straight. So suppose that this is E2. So this is a stable eigenspace, but we will call it fast. Okay, so this is the fast, and this is the slow. So this would be E1, okay, which is a stable eigenspace, but it's slow. So any trajectory, so again, they're both stable, so we'll draw lines converging to the equilibrium point. But if you are to follow your system, this will behave in this particular way. So you see that now the slow subspace, or sometimes called manifold, will be attractive for all trajectories, and even here. Okay? So this would be a stable point, stable equilibrium point, sometimes called, stable node. And this, as I said before, is a saddle. Okay? But in any case, what the important thing is that we have highlighted, if I could somehow highlight. Okay, well, forget it. This is the, I'm really sorry about this, but it's totally impossible. It's totally impossible to write down a straight line. It's unbelievable that the biggest problem we have is to draw straight lines. Okay, now I'm putting a piece of paper. Okay, so you see this manifold here, or this subspace here, and this other subspace here. this one, okay? They represent the asymptotic behavior of the system, the system at t going to infinity. So for long times, okay? The system will live on this subspace, okay, for very long times. And in fact, it will exhibit only the slowest time scales, okay? Or in this particular case, the slowest time scales. Or in this particular case, it's the most unstable time scale, okay? And exhibiting only one time scales of the n that you have, the system clearly is non-stiff. So you're beginning to see now a pattern where essentially we're trying to view the system in its asymptotic behavior as a system that lies on a smaller dimensional subsystem. In this case, you see it's this eigenspace here, it's one dimensional, and will only exhibit one timescale, or at least a subset of timescales that are closer together, that are slow. So this is what we're going to look at in the future, simply because you have a stable equilibrium point, okay? In chemical kinetics, you're never going to diverge towards infinity like this, okay? In these systems here, you're always going to go to the equilibrium point. Okay, so these are more interesting dynamical systems. Of course, again, I remind you, they're linear. Okay, so we use them to define, okay, a set of analytical tools. But clearly, now we're going to have to make the shift towards non-linear systems, unfortunately. But what's important to understand is that a system eventually will evolve along a smaller dimensional system, okay? E slow. We can call this a slow manifold. Okay? And the system will be non-stiff in the sense that it will not exhibit all of the timescales, but just the slowest ones. Okay? This has advantages because essentially, well, if you want to integrate a system, which is very hard to integrate, you could just take the asymptotic behavior. If you know the manifold, and in linear systems, obviously you know, but clearly in linear systems, you know everything, okay? And so it's a little bit useless. But suppose you have a nonlinear systems and you know the slow manifold, then you know that the asymptotic behavior of the system will be constrained on this slow manifold and will only exhibit a subset of very slower timescales. And so it will be lower dimensional because clearly constrained in a lower dimensional manifold, and will be non-stiff. So you have a double advantage, okay? Now these are, and I'll stop here, but these are a bunch of techniques that are very common in combustion, okay? That tend to characterize, okay, this dichotomy between fast and slow, okay? When you have these very fast intermediates that are produced and very fast or very rapidly produce a pool of radicals, which finally will decay and oxidize towards H2O and CO2. So you will tend to look at the slow evolution and not to that very fast temporal boundary layers. By the way, what's a temporal boundary layer here? Well, it's everything that's outside the slow manifold, clearly, because this is where the fast timescales are actually acting. So you see, outside of the slow manifold, you will have these trajectories which very rapidly collapse. And then the outer solution, in fact, is this highlighted region where you have only the slow time scales. Okay, and this try to sort of absorb this, because this is a vision of dynamical systems, is an approach that's really applicable to everything, many aspects of engineering. Let me just close with the final argument by saying that by looking at these pictures, you see that stability for linear systems is a global concept, is extended all throughout the space, okay, the phase space. Why? Well, because your invariant subspaces are flat, so they extend infinitely. Now, the very big difference between linear systems and nonlinear systems, and what makes nonlinear systems so much more complicated, is that these invariant subspaces, they do exist, but unfortunately, they're curved. And they tend to curve very rapidly on each other and form basins of attraction and form all kinds of things. So trajectories are definitely more complicated, and stability is not known throughout the phase space, but only locally. Okay, so that's the big difference and the big separation. But these concepts of timescale separation, we will see there is a link with a so-called Hartmann-Grossman theorem, and we'll be able to actually define most of the concepts, especially the slow manifold concept, also for nonlinear systems. Okay. Okay, I will stop it here. I hope you can still hear me. There are some survivors.
Yes, Professor.
Oh, good. So I will stop the recording.